made a prediction that was unconstrained by our result, right? It was just using their best physics inputs that they had, right? This is our knowledge of the structure of U8. Low by a factor of 2.5, okay? Which is horrifyingly bad for something that we should know this well. So we went back to the dance data and said, wait a minute, we have all of this gamma ray information. Let's put in the structure ingredients that went into this reaction rate calculation and stick them into something that predicts what the gamma rays look like, right? Because I can do this, right? These things can be coupled in this way. And essentially the spectrum that we saw was completely wrong. It was horrifically broken, okay? So you can start looking at, well, what went into this? What were the nuclear structure bits that could be missing? And you can come up with physics arguments about this particular M1 scissors resonance, which is stuff no one needs to care about what that means. And you can stick this ingredient in and start playing around with the knobs, all right? And you can then get satisfactory reproduction of the gamma ray spectra that we saw, right? And you say, oh, okay, well now let's test whether or not I've improved my understanding of the structure by feeding my new structure information back into the reaction rate calculation. I nailed the cross-section to 10%. So, yeah, it worked. And so that's why there is a number of experiments we run every year, mostly in collaboration with universities that have no other purpose than to look at the nuclear structure parts. Like they'll take capture data, they don't care about the capture reaction at all. Like they don't care about the cross-section or anything like that. They want to use it to populate that piece of the nucleus to study its structure. And so that's a whole piece of what we do these days. Mm-hmm. Yeah.
So you mentioned uranium and plutonium, and those are familiar with why you'd be looking at them. But are there any other elements that you're looking at for particular reasons that?
Yeah.
Yeah.
And some of them are just for applications reasons. Some of them are not. So one of them that I have a project working on is zirconium-96.
Yep.
And the reason for that is a thing that I completely glossed over for the interest of time, is that fission blows the nucleus into two pieces, right? Well, these are nuclei. What are they? These are what we call fission products. And they have a distribution. There are many different possibilities. And it turns out for nuclear structure reasons, there's a light one and there's a heavy one. It's not symmetric, okay? So you blow into a piece that's much lighter than the other piece. And so you have these two humps in the mass yields, right? So how heavy were the two pieces that I made? It turns out that the light mass yield peaks near zirconium. And so, given that that's a place where you make a lot of stuff burning nuclear fuel, it's reasonable to say that you would want to, for the sake of applications, understand capture in that region. And so we are in the process of doing an experiment on zirconium-96 that's actually stable. We did one at DANCE, and we're doing one with Apollo as well. Same beam, trying to study the same nucleus, for the express purpose of figuring out whether in that region with its particular unique nuclear structure, we actually get the same answers between the DANCE measurement and the indirect measurement, because no self-respecting program manager is going to let you take an untried tool and go predict something for the program. So we're going to prove that we know what we're doing, and then we can look around there and do things for applications. So that's one. The other thing that a colleague has funded, not me, this is actually a very interesting story because it proves what I was saying about the tie-in between astrophysics and applications. So the idea here is that iron-60 is something that you observe in the galaxy, and it has only a million-ish year half-life. And so it is a diagnostic of active nucleosynthesis in the galaxy. And there are not many of those, okay? And so this is potentially very interesting for astrophysics. The problem is that right next door to iron-60, as in the way that you make it, is capture on iron-59. Well, iron-59 has a 45-day half-life, which means essentially you can't do a direct measurement because it lives for too short a time and emits nasty radiation that kills any detector you try to measure capture with. And so this is a perfect use of this Apollo technique to do an indirect constraint of the capture cross-section for this. Because essentially if you cannot understand quantitatively the production mechanism of iron-60, you can't do anything quantitative for stellar nucleosynthesis in this particular thing and use this diagnostic to actually do things and improve models, right? And that's what we actually want to do fundamentally. So we have an LDRD, ER, that is doing a number of things. And one, it's using dance to look at the stable ions and understand their structure. And then we're in the process of getting the experiment run on the iron 59 itself, okay? And that's all great, and that is for astrophysics. But in the meantime, some folks from the program side said, wait, you're looking at iron? That's interesting, because iron's in steel. Steel's in lots of stuff. Shocker. And so they're actually looking at adding in their own experiments to the campaign. So essentially, the LDRD will run its course and it'll answer what it did for astrophysics. And then we will tack on other things that have no relevance for astrophysics, but they are of interest to the programs. But the fact that the project existed was why there was a talking point with the program, because the people there didn't actually realize that we were capable of answering the question in the first place. So they were just accepting this will just remain an open question.
So what are some of the interesting things you might find out about iron that's in a lot of things from the work that you're doing? Like what advances could we see practically?
So there's a couple of different things, some of which are more esoteric than others. The least esoteric is that, well, there's this whole astrophysics side thing where essentially if you want to actually use iron 60 in the observations that people have now to try to pin down what's going on in models, which have many free parameters, right? And the problem with these large-scale multi-physics models is that there are so many free parameters and knobs that you can tweak in so many places that you can get compensating errors that wreck everything. Essentially, you can get the right prediction for completely the wrong reasons, which means that you have a descriptive model, not a predictive model, right? And scientists hate that, right? And so you remove from this one particular piece, right, that people want to actually do something productive with but currently can't really, you remove that knob, right? And that puts them closer to an actually good footing to do something predictive, okay? And the other thing is, well, steel's and all kinds of things. You expose it to neutrons, and you can infer the neutron bath, the environment, whatever, that it was in. That's the application side. And pretty much I think that I have to stop there because of rules.
Okay. I don't want you to
Yeah, I'd rather not get
rules.
fired. Yeah.
So going back to astrophysics, I'm sure you're keenly interested in the S process and the R process for
Yep.
nucleosynthesis, and so the branch points where beta decay takes you up in Z and,
Yep.
and capture takes you up in A.
Yeah.
Those are of particular interest, I believe?
Yes.
Are there particular isotopes that that you're studying for that application?
So not I, but a collaborator from LSU. So this actually is a separately interesting thing because I don't know who's in the room, but there are various things that NA22 and NNSA does to try to garner interest amongst graduate students, right? Expose them to national labs, get them thinking about a career here and so forth. And what I'm about to describe came out of one of these. So we had, it was part of, I think, the SSAA at the time was what it was. There's several of these grants and I can't keep them straight. But there was a graduate student working at LSU who was looking for a 3-month practicum. That was a requirement of this process because he was getting his funding through NNSA or NA22 or some such. And so he came out and worked with us at Lance on DANCE, doing digital signal processing to make a detector work. Okay, that it wasn't correlated with where things ended up. But in the course of being there for 3 months, he became very interested in what we were doing and didn't actually have a thesis project. And we started looking around and said, wait a second, we could do something for a zinc isotope. Actually, there's 3 zinc isotopes. I can't remember which one specifically, but there's an S-process branch point in there. And understanding the whole suite lets you figure out what the behavior of that is, and it more or less drives what's going on with